two variables with respect to each other.
Sorry, yes. So basically finding the slope, or it can also be defined as essentially taking a large quantity and breaking it down into infinitely small pieces. And in this case, that's how we find the slope, because we break down a curve into infinitely small points. And thus, we use integration to find the slope or to find instantaneous velocity or acceleration. And I'm pretty sure the grade 11 students will be familiar with this, or at least will get familiar with this during the rest of their year. So differentiation is usually used for things like that. Now, integration, we can say, is essentially the opposite of differentiation, whereas differentiation was finding the value of, you can say, a quantity at a specific small point. Integration is essentially joining or integrating the values of all of the function and all of the small points to get a larger value over an area. So if we think of it as, for example, like we said, we use differentiation for slope of a graph. So for the slope of a graph, since we use differentiation, if we integrate the graph, we will get the area under the curve of the slope. Moving on, so we can, if once you guys have gotten a basic understanding of integrals. So once again, I'll repeat, integration is the act of integrating or joining many infinitesimally small points to get a larger value. Or it is also the practice of finding the area under a curve of a graph. And it is also the antiderivative, or the opposite of finding a derivative, or the opposite of differentiation. Moving on to the second page. Well, here we go more into depth of integration as an inverse process of differentiation. So as it says here, integration is the inverse process of differentiation. Instead of differentiating a function, we are given the derivative of the function and asked to find its primitive. So primitive is essentially the integral of a differentiated function, or the original function that is usually given. So that's another name for the original function before it has been differentiated. And obviously, since integration is
भाई देखने
an
तो दो
inverse.
नीचे जा रहे
Sorry?
हैं ना पार्टिसिपेंट वहां से देख रहे हैं
वो सारा उमेर अदनान
Apologies for the disturbances. Now,
It's all right.
so as we said, integration is an inverse process of differentiation. So let's say, for example, we want to find the integral of cos x. So we need to find a function whose differential is equal to cos x. And we know from differentiation that sin x, the differential of sin x, is equal to cos x, right? So when we differentiate sin x, we get cos x. And to find the antiderivative of it, when we integrate both sides, we'll see that the antiderivative of cos x is equal to sin x, because the original function before differentiation is sin x, and after differentiation it is cos x. So when we integrate, we will get the primitive of cos x, which is sin x. Similarly, there are some other examples like x cubed by 3, which becomes x squared. And here, if I'm able to annotate, I'll actually explain this, how they got x cubed by 3, basically. Here in this question, we know that one second. We know from differentiation that x cubed, differential of x cubed, d of x cubed by dx, is equal to 3x squared. Now, if we want to find the antiderivative of x squared, we have this extra 3 value here. So this actually goes under x cubed. That's why we get d by dx of x cubed by 3 is equal to x squared. So antiderivative of x squared is x cubed by 3. And I mean, if we look at it normally as well, if we, for example, differentiate x cubed by 3, so that will be, as we know, a constant comes out, x cubed 1 by 3 into x cubed, differential of x cubed, and this will give us 1 by 3 times 3x squared which will be equal to x squared, which is our antiderivative right here. So essentially, these examples show you that integration is an inverse process of differentiation and how to find the antiderivative of a given function. Now, one thing to note here is, and again, I think the 12th graders will have a little more of an idea on this, but we know from differentiation that we've learned in 12th grade that the derivative of e raised to the power x is equal to e raised to the power x. Therefore, since the differentiated function and the original primitive function are the same, that's why the primitive of e raised to the power x will remain the same, which is e raised to the power x. There will be no change, as we can see in this example here. So another thing, so essentially that was what integration as an inverse process of differentiation is. Now let's read what this says here down in NCERT. So it says that we observe in the first equation, which is the differentiation of sine x is equal to cos x, the function cos x is the derived function of sine x. We say that sine x is an antiderivative or an integral of cos x. And this is again because if we integrate cos x and integrate sine x from both sides, then, and in fact, oh, I don't have my video on, my apologies. So if we integrate sine x and cos x, we integrate both sides, we will get integral of cos x is equal to sine x. And the reason we will come to is another property of integration where the differential operator and the integral operator usually cancel out because they're opposite or inverse functions. So then it says, similarly in 2 and 3, x cubed and ex are the antiderivatives of x squared and ex respectively, like I explained. Again, we note that for any real number c as a constant function, its derivative is 0. Therefore, we can write 1, 2, and 3 as sine x plus c is equal to cos x, and x cubed by 3 plus c is equal to x squared, and e raised to the power x plus c is equal to e raised to the power x. Now here, basically what they're saying is, since when we differentiate a constant function, its derivative becomes 0. So these functions can also be written as a function which essentially with a constant, or in which a constant has been added, because the constant will not affect the differentiation of the function. And we will see the significance of it in this next paragraph. Thus, antiderivatives or integrals of the above cited functions are not unique. Actually, there exist infinitely many antiderivatives of each of these functions, which can be obtained by choosing c arbitrarily from a set of real numbers. For this reason, c is customarily referred to as an arbitrary constant. So what they're saying is, for different values of c, if you see, and I'm sure maybe Umair has some insight on this. If we look at it graphically, for different values of a constant in a function, the curve of that function will be offset by that constant. So let's say if we have, let's say for example, if we have a function that is x squared, and we know that the graph of x squared, if I were to draw it here, is a parabola. So it comes like this, and it goes up like this. Obviously, this is not a pointed point, it's somewhat of a round point, but it usually, if y is equal to x squared, then this curve has its vertex at 0. Because if we put y as 0, and that means x squared is also equal to 0 squared, which is equal to 0. Now, if we were to add an arbitrary constant here, say 1, now if we put y as 0, this is essentially what we did here, is calculating the x and y intercept. Now, if we put 1 here, then if we put x is equal to 0, then we get y is equal to 0 plus 1. So now, even though the differential of both of these functions, y is equal to x squared and y is equal to x squared plus 1, will be the same, the graph of y is equal to x squared will be offset by 1 on the y-axis. So now, let's say this is 1. The vertex of the graph will be at 1, 1, not at 0, 0, 0. So essentially what they're saying is, since the constant does not affect the differentiation, there can be infinitely many functions that will give you the same derivative. And these can be obtained by adding different values of c. So like it says here, actually there exists infinitely many antiderivatives of each of these functions, which can be obtained by choosing c arbitrarily from a set of real numbers, and therefore we call it an arbitrary constant. In fact, c is the parameter by varying which one gets different antiderivatives of integrals of given functions. More generally, if there is a function capital F such that d of capital Fx is equal to Fx for all x belonging to I, which is an interval, then for an arbitrary real number c, also called constant of integration, which we will see further ahead, then d by dx of fx plus c is equal to small fx for x belonging to I. Yes, Umair, go ahead.
Excuse me. I was wondering if can you tell me the meaning of C? Because I was actually a little confused about C.
C is essentially any constant variable or constant function, not a variable, a constant function that we add to a function, and when we derive it, it becomes 0. It's essentially just a constant, or it's also
okay,
called the
that clears
constant of
it.
integration. Yeah.
Thanks.
So, and we can see here in this example, it says, let's say the derivative of fx is equal to x, small fx. So if we add c, we know from differentiation that c is a constant function, and derivative of a constant function will be 0. So then c does not affect the derivative of this. So moving on. So it says f plus c and c belonging to R denotes a family of antiderivatives of fx. And then this is an extra bit which says functions with same derivatives differ by a constant. To show this, let g and h be two functions having same derivatives on interval I. So we know that f is equal to g minus h is defined for fx is equal to gx minus hx. When we derive this, we get f dash x minus g dash x is equal f dash x is equal to g dash x minus h dash x, and then we get 0 because the difference between this is a constant, so we get 0. And that means that i.e. the rate of change of f with respect to x is 0 on I, and hence f is constant, because we're given that the functions with same derivatives differ by a constant. To show this, let g and h be two functions having same derivatives on interval I. And essentially f is a difference. So we know that f is a difference. So when we say f of x is equal to g of x minus h of x, and then when we differentiate it, we know fx is constant. Therefore, the differentiation of fx is equal to 0. Then we introduce a new symbol, namely integral of fx dx, which will represent the entire class of antiderivatives read as indefinite integrals of fx with respect to x. Here I want to touch on another point. There's two types of integrals, which are definite and indefinite integrals. Now, definite integrals are integrals from a limit to another limit. So between a given interval, that means, and we will see this further in the chapter, although I'm not sure if I'll be able to get there today. But it essentially means when you integrate a function, you are integrating it in a closed sort of boundary. And there's different limits which you have to apply to get the value of that function. An indefinite integral is one where there's no limits. So it is just a general integration. And it deals with the entire, you can say, entire class of antiderivatives, which means all the infinitely many antiderivatives that we can obtain by varying c. It is the integration of all of those, whereas a definite integral is more towards a specific subclass between the entire class of antiderivatives. So, okay, Adnan, go ahead.
So it's like a surface integral from like physics, like a closed interval?
If let's say, for example, if it's given to us, like, for example, we want to find a surface integral for a sphere, then we do the surface integral of 4 pi r 0 to 4 pi r squared, right? of a sphere. So this will be termed as a definite integral because it is not an integral which is dealing with the entire class of derivatives. It is dealing from limit 0 to limit 4 pi r squared. Therefore, this, okay, there's two questions. Okay, go ahead.
I was wondering what's the meaning of the symbol that you wrote. It looks kind of different to the one that
Yeah, this is
we're
basically a
supposed to look
closed
at.
integral. So a closed integral means an integral over a closed surface. This is more of a physics question. But
All right.
basically, yeah, it's like a closed surface. I think, Omer, do you have another question? Because you have your hand raised. Okay. Adnan, I think you had a question as well, right?
Yeah, it's clear now. I got it.
Okay. And so moving on, so basically indefinite integrals are those that do not have a limit and they deal with the entire class of antiderivatives of a given function f. Now, here are some terms and some essentially phrases which we'll be using. So obviously, as seen above, when we put this symbol, which is called the integral symbol, this will be the integral of f with respect to x. 1 second. Okay. So integral of f with respect to x will be denoted by this symbol. So this is the integral symbol, and this is the function f, and it's with respect to dx, so x. Similarly, the fx, or the function that is being integrated, is called the integrand, which is inside the integral. And x is obviously the variable of integration because this is the variable that varies and has different values. And this is the different values of this variable is what we are trying to integrate. Now, I keep saying integrate, and integrate essentially just means find the integral of something. So you'll be hearing me use that a lot, and it'll be in the questions as well. It's just commonplace where they say integrate this function, which means find the integral of this function. Integration obviously is the process of finding the integral, and constant of any of integration is any real number considered as a constant function. Now, again, I want to touch on this a little more because it might be a little confusing. The reason we put the real number c, or constant of integration, is because when integration, like we said, is the antiderivative of a function. Now, as we saw, c does not affect the derivative of a function. So while we do integrate a function to find the antiderivative of that function, or the primitive of that function, if we don't add a constant of integration, we do not take into account any constant values that were in the original function. So c is essentially taken essentially take into account any constant values in that function, so that our function that we get from integrating is not different from what we would get what the actual function is basically. So like I said, the integral of y is equal to x squared and the integral of y is equal to x squared plus 1 will give you the same integral. However, their graphs are different. Therefore, c is taken to account for that 1, basically. So to account for any constant functions in the original or primitive function, we take c. So moving on, now we come to the sort of the formulae part, and essentially we'll just go through these. Most of them are actually trigonometric identities, or trigonometric integrals of trigonometric values. But especially for 11th grade, some of the more useful ones would definitely be the first one, which is here. If I can annotate, 1 second. If I can annotate, this is what most of the physics and chemistry derivations use. So it is just the integration of x raised to the power n. So now this integration of x raised to the power n here is any real number, or so any real number. So it can be a fraction, or it can be a negative number, or anything. So essentially, x raised to the power n is equal to x raised to the power n plus 1 divided by n plus 1. So it is the new power divided by what the value of the power is. So let's say if we have, for example, integral of x squared dx. using the value here, we get x raised to the power 2 plus 1 divided by 2 plus 1. So this is equal to x cubed by 3. If you would just give me one moment, please bear with me. All right, coming back to what we were discussing. So essentially, that is the first formula. And also the second formula that is important, which, I mean, all of these are important, but the second formula that we will be studying is that this formula, d by dx of x. So here it's giving the analogy between these two, right? So essentially, we see the derivatives and we see the antiderivatives of integrals. So now we know that d by dx of x is equal to 1. So d by dx x of x is equal to 1. So antiderivative of 1 will be equal to integral of this and this cancel out. So antiderivative of 1 is equal to x. So that's, and obviously we put the constant of integration, which is c. So this is the second identity. Likewise, we have all of these other identities, sine x, cos x. I would like to take into account this identity where it is cos x and sine. Now we know that the integrate or the derivative of d by dx of cos x is equal to minus sine x, right? So now there's an extra minus sign. So what we do is we take it to the left, and when we integrate, we will get integral of sine x is equal to minus cos x. Now this is because we took this minus sign to the left-hand side and multiplied it by cos x. So just remember that for any of the, let's say, derivatives which have a minus, which, give a minus sign, you usually take it to the right to the original function in the integration of the function. So likewise, I believe we can see it for some other ones as well. So like, for example, minus cot x equal cosec squared x, because we know cot x is equal to minus cosec squared x. So then we take minus to the right side. So minus cot x will give us cosec squared x. And of course, we also have the antiderivatives of certain inverse trigonometric functions. Again, this is just playing off of what we learned in differentiation. So for example, we know that the derivative of sine inverse x is equal to 1 upon under root 1 minus x squared. So then that means that the integral of 1 upon 1 minus x squared will give us sine inverse x plus c. And similarly, we can see all of the the integrals of the functions. Again, here the minus rule applies because we know that the derivative of cos inverse x is equal to minus 1 upon 1 under root 1 minus x squared. Therefore, again, we take minus to the left-hand side to cos inverse x. So therefore, when we integrate 1 upon 1 minus x squared, we get minus cos inverse x. So moving on, we also have certain other, these after the trigonometric identities, these certain identities are also important when we talk about these integrals right here. Forgive my messy writing, but yeah, these integrals are also important, especially when we talk about e raised to the power x, because as we saw before, the antiderivative of e raised to the power x is equal to e raised to the power x. Therefore, there is no change when it is differentiated or integrated except for plus c, obviously to try to take into account any constant functions. Now, give me 1 second. So these are some other integrals. And I would also like to take into account this, 1 second. I would also like to take into account this identity. So now we know log x, differential of log x is equal to 1 upon x. But what can you say of the differential of log of minus x? Anyone? What is the differential of log of minus x?
I'm not sure. Is it minus 1 by x?
Wait, it's not defined, right? Because log is not defined for negative values.
Exactly.
Oh yeah, that's true.
Therefore, we always take mod of x for log. So whenever we put log of anything, it has to be a positive value. Therefore, we take log of mod x. So in case any, for example, we have any negative value, we get the log of it and we put it in mod, so we get a positive value for which it will be defined. And so therefore, again, with the antiderivative, we know that the derivative of log x is equal to 1 upon x. So then the same way, the integral of 1 upon x will be equal to log of mod x plus c. Okay, moving on. Geometrical interpretation of indefinite integral. Let's read this first and try to make sense of it.
Hello.
Yes. Abrar, is this Abrar?
Yeah. Can you hear me? Yep, it's me.
Yes, you are audible.
Thank you.
Okay. So the geometrical interpretation of an indefinite integral is essentially, so let's read what it says. Let fx equal to 2x, then integral of fx dx is equal to x squared plus c. Because we saw, okay, so this is actually a good sort of introduction point. I want you guys, looking at the formulas that we saw before, I want you guys to solve this. It's a very, very simple problem. Find the integral of x squared. Or no, sorry, find the integral of 2x dx. I want you to tell me what the answer is. I mean, obviously, you probably already saw it, but I want to know the reasoning behind what you guys said, or why you chose your answer.
If we integrate that, it will result in 2 into x squared by 2.
Okay, so how exactly is that possible? Which formula did
2
you
into
use?
integration of x.
Yeah,
That will
which
be x
formula did you use?
n plus x to the power of n plus 1 by n plus 1.
Exactly. So, like Abrar said, when we integrate 2x, for an integral, a constant function like differentiation can be taken outside. So it'll be 2 times integral of x dx. Similar to integration, the constant function, if it's in multiplication, can be taken outside. So when we integrate this, we have essentially the integral of x. So we can write x as x to the power 1. So when we use the formula x to the power n plus 1 upon n plus 1, we know that the value of n is 1. So this becomes x to the power 1 plus 1 upon 1 plus 1. So this is x squared by 2. But remember, we have this constant value here too. So when we multiply this 2 and this 2 gets canceled. So we get x squared. And then obviously, for all integrals, you have to include the constant of integration. So that's essentially what it says here. That let fx equal to 2x, then integral of fx dx gives us x squared plus c. For different values of c, we get different integrals, but these integrals are very similar geometrically. Thus, y is equal to x squared plus c, where c is an arbitrary constant, represents a family of integrals. By assigning different values to c, we get different members of the family. Like we saw before, the reason there are infinitely many antiderivatives of a single function is due to the variation in the constant value c. So that's essentially what they say here. By assigning different values to c, we get different members of the family, which means different members of the class of all antiderivatives of that function. These together constitute an indefinite integral. Again, going back to what we studied, we saw that an indefinite integral deals with all or the entire family or the entire class of antiderivatives that are obtained due to variation in C. In this, so these together constitute the indefinite integral. In this case, each integral represents a parabola with its axis along the y-axis. So actually, this is the exact example I gave you guys before. So x squared, as we know, the function will have a parabolic curve. And this is where I was talking about the offset. For different values of C, the vertex will be at, for example, 0, 1, 2, etc., etc. So that's what it explains in the next paragraph, which says clearly for C equal to 0, we obtain y is equal to x squared, a parabola with its vertex on the origin. And this is because putting x and y 0 separately in the equations, we get that the x and y intercept for this parabola, and since it has no constant function, both x and y will be 0, therefore its vertex is on the origin. The curve y is equal to x squared plus 1, however, for c equal to 1 is obtained by shifting the parabola y is equal to x squared 1 unit along the y-axis in the positive direction. Now, again, this is because, like I said, c, or the constant, gives us a offset to the graph. And in this, we can see if we were to calculate the y-intercept, can anybody tell me how we calculate a y-intercept? Okay, so it's all right if nobody maybe not be recalling right now. Basically, the y-intercept is where the graph cuts the y-axis. Now, what is the equation of the y-axis? Does anyone know? Bro, I think if you're trying to answer, I think you're still mute. But if you're not trying to answer, then
No.
okay. So the equation of the y-axis, what is the common feature of y-axis? On the y-axis, all x are equal to 0. This is the equation of the y-axis, because at any point of the y-axis, the form of that point will be 0, comma y, right? So to find the intercept of the y-intercept, basically what we do is, since the graph is cutting the y-axis, any point on the graph where it cuts the y-axis will be 0, comma y. So basically, putting x equal to 0 in the given function or equation, in this case, we get y is equal to x squared plus 1, will give us the y-intercept. Now here, y is equal to 0 squared plus 1, so y-intercept is equal to 1. Therefore, like it says here, for the curve y is equal to x squared plus 1, for c equal to 1 is obtained by shifting the parabola y is equal to x squared 1 unit along the positive direction of the y-axis, because the y-intercept is 1. So that is where the vertex will be. So similarly, for different values of c, you get different vertices. Thus, for each positive value, each parabola of the family has its vertex on the positive side of the y-axis, and each negative value has it on the negative side of the y-axis. Similarly, let us consider the intersection of all these parabolas by a line x equal to a. In figure 7.1, which I believe will be below this. Give me 1 second. Yes, this is figure 7.1. We have taken, so it is talking about how the intersection of all of these parabolas by a line equal to a is x equal to a. So in this figure, they've taken, obviously, a is greater than x, so it's on the positive side of the x-axis. So what are they saying? Let us consider the intersection of all these parabolas by a line x equal to a. In the figure 7.1, we have taken a greater than 0. The same is true when a is less than 0. If the line x equal to a intersects the parabolas y is equal to x squared, y is equal to x squared plus 1, and etc. at p1, p0, p1, p2, etc. It's respectively, then dy by dx at these points is equal to 2a. Now, why? Can you tell me why exactly that is? Can anyone tell me that? Why will we get 2a, the derivative of these functions?
Because they are parallel.
Well, I mean, no. If we look at it mathematically, we know that the given function is y is equal to x squared. And for all of these other functions, we see it's y is equal to x squared plus 1 plus 2, which are all constant functions. So the derivative dy by dx will always give us 2x. But the reason we get 2a is because the intersection of all these points is at a line x equal to a. So therefore we get 2a because we substitute x equal to a. So this indicates that the tangents to the curves at all these points are parallel, like Omer said, yeah. Thus, 2x integral of 2x dx is equal to x squared plus c, which is equal to fc of x, implies that, what does it imply? The tangent to all the curves y is equal to fc of x, where c belongs to r, at a point of intersection on the curves are parallel. So all of the tangents, like Omer said, are parallel. Because they all give us the exact same slope because their derivatives are equal. Further, for the following equation or statement, fx dx integral of fx dx is equal to fx plus c, which is equal to y, represents a family of curves. The different values of c will correspond to different members of this family, and these members can be obtained by shifting the curves parallel to itself, the geometrical interpretation of indefinite integral. So this is what they said. Now I'll try my best to explain it. Basically, they're just showing you the geometrical, or they're trying to show you how indefinite integrals are formed. So now we can see that the derivative of each of these functions, x squared plus 2x, x squared plus 3, x squared plus 1, x squared minus 1, all of them give us the same slope, which means all of these graphs will be parallel. However, the difference is that each of their c makes a different graph. So now the family for all constants of y in the function y will give us different graphs. And an indefinite integral is essentially the integral of all of these different graphs that are formed. So basically, every single graph that is formed will be constituted